and welcome to Arithmetica. This video marks the first episode in our program covering an introduction to propositional logic. In this video, we consider the language used in mathematics, before concluding with a simple proof from a proposed conjecture. Over the centuries, mathematicians have derived numerous results, often of some significance. Such results are statements which have been shown to be true by deductive reasoning and can be traced back to basic principles of mathematics called axioms. Thus, all results in mathematics are the true conclusions which have been logically derived from accepted truths. We often use the words premise or deduction in mathematics. In a separate video covering proof and reasoning in mathematics and the sciences, we introduced early on deductive logic, where we explained that a premise is simply a proposition from which a conclusion can be derived from. Thus, we often use the words premise and proposition interchangeably. Another word, which is sometimes used instead of premise, is statement. Consequently, during the most part of this and subsequent videos, we shall be using such words as premise, proposition, and statement interchangeably. Now, in logic, a premise, proposition, or otherwise a statement is a sentence which has an unambiguous interpretation of being true or false. Thus, sentences like, "How are you today?" and "Please take care of yourself" are not statements, whereas sentences like "This is a fish" and "5 is greater than 3" are statements, since regardless of one's knowledge of fish or that of numbers, there exists a notion of being true or false. And so propositions are those sentences that we can assign a truth value, which is either the truth or the false. A logical deduction, on the other hand, is the formal process where a conclusion is obtained from known statements in force. We often describe logical deduction as truth-preserving. This is because deductive logic is characterized by what is known as logical validity. In the aforementioned video, where we introduced the basic concept of deduction, we defined logical validity as where the truth of the conclusion is guaranteed on the proviso that the premises in force are true. In many situations, if new results are sought from a particular branch of mathematics, then a process of analysis will often include some special cases of interest first. Mathematicians are frequently referred to as pattern hunters. This is because of the investigative nature of the analysis, which can reveal mathematical structures or patterns where a mathematician may be able to establish a possible rule. Such a proposition is called a conjecture. It is now the job of the mathematician to ascertain a logical process in deducing its truth, thereby establishing a mathematical proof of the statement. With the successful completion of a mathematical proof, we can then elevate the conjecture to the status of a mathematical theorem. As a simple example of a conjecture in mathematics, suppose the following pattern of adding two odd numbers together is observed. From this, it could be conjectured that the sum of any two odd integers is even. But how do we know that this is true? After all, we have not tried adding together all possible pairs of odd integers. To prove this, we require a way of expressing mathematically arbitrary even and odd numbers. And indeed, there is a way to do this. Let n be an arbitrary even integer, then we may write, without loss of generality, n is equal to 2 times q, where q is some integer, and let n be an arbitrary odd integer, then we may write, again without loss of generality, n is equal to 2 times k plus 1 for some integer k. In our introduction to number theory, we should provide an explanation as to why this general form of even and odd numbers is justified. But the simple answer is, on dividing by 2, even and odd integers have a remainder of 0 and 1 respectively. We now prove the conjecture that the sum of any two odd integers is even. Here's the proof. Let n and m be two arbitrary odd integers. Then there exists integers p and q such that we may write n is equal to 2 times p plus 1 and m is equal to 2 times q plus 1. Therefore, n plus m is equal to the sum of 2 times p plus 1 and 2 times q plus 1 by definition. We can write this as 2 times p plus 2 times q plus 1 plus 1. Let's simplify that a little, adding the ones together. Quite superficial simplification, however, but that factorizes by 2, so we obtain 2 all multiplied by p plus q plus 1. We can write this as a somewhat simplification as 2 times r, where r is an integer. The final step in the equation is using the fact that the sum of any two integers is also an integer. This is known as closure. That is, the set of integers is closed under the binary operation of addition, together with the property of associativity. Thus the result follows. Thus n plus m is equal to 2 times r, where r is an integer. But 2 times r has the form of an even number. Moreover, since n and m by hypothesis are arbitrary odd integers, we deduce that the sum of any two odd integers is even, as required. Thus we have now proven the conjecture to be a mathematical theorem. However, strictly speaking, the term theorem is usually reserved for a key result, one which is of significant importance. Other terms of a derived result in mathematics are lemma and corollary. A lemma is generally considered to be a minor result and are often used to derive theorems, whereas a corollary is simply a result which follows immediately from another already established result. Thank you for watching Arithmetica's first episode introducing propositional logic, where we provided some of the formal language used in both mathematics and propositional logic. In the next video, I will detail the structure of sentences and how they can be combined. I have also created a complementary video to this episode consisting of a few exercises. They largely function as a sort of checklist for what I have covered in this episode, introducing propositional logic. Feel free in clicking on the annotation or on the link in this video's description. And so until next time, it's goodbye from Arithmetica!